Greetings, AP Calculus students, to day 2 of our discussion of the topic of optimization. In our previous lesson, I introduced to you guys this idea of using derivatives to maximize and minimize quantities and contexts. Now, obviously, this idea of finding maximums and minimums is not something new to us. We've found the maximums and minimums of functions before. This time around with optimization, though, we see how we can find the maximums or minimums of functions in more contextual situations. And not only that, but we also saw how typically in these types of problems, we have two different sets of equations that we have to use together so as to make a single equation of only one variable. So today we're going to look at a few more examples. We're not necessarily going to be looking at any new aspects of it. We're just going to be looking at a different set of examples today in today's lesson. Before we get to that, let's try our bell ringer, which is just a little bit of a review of finding some antiderivatives. So we're given f prime of x, that is equal to cosine of 2x. What is a potential equation for function f? So we're given the derivative of function f, and we are asked to find the original function f. All right. So remember, we're working backwards. We're working backwards here. All right, so, well, let's see. So our derivative is cosine. So let's see, what function's derivative is cosine? What function's derivative is cosine? Well, hopefully, you said sine. Sorry about that. Hopefully you said sine, right? The derivative of sine is cosine. So the derivative of sine is cosine. Okay, so we have that function. Well, let's see if that function works. So sine of 2x. Sine of 2x. So let's test this answer. So f prime of this would give us cosine of 2x, but we would have to use the chain rule and multiply by the derivative of the inside function 2x. So that gives us 2. Well, we don't want a 2 in front of this equation because the original equation the derivative equation has no 2 in front of the cosine. Well, we can easily take care of a 2, can't we? We just have to add a 1/2 to it. I'm sorry, not add a 1/2, but multiply by 1/2. So let's try instead f of x is equal to 1/2 sine of 2x. Let's see if that works. So let's test this one now. So f prime of x would be equal to 1/2 cosine of 2x. And then to eliminate that 1/2, we would have to use the chain rule by the derivative of the inside function, and doing that gives us a multiplication by 2, and 1/2 and 2 just cancel out because you just end up with 1. So it looks like our answer does indeed work of 1/2 times sine of 2x. Now, this is actually not the only correct answer. There are other correct answers that would give us this derivative function. Other correct answers, for example, we could have also had, we could have also had 1/2 sine of 2x plus 3. We could have also had 1/2 sine of 2x minus 5, and so on and so forth. We could have added or subtracted by any constant because going forward or taking the derivative of this function, that constant would just become 0, right? The derivative of a constant is always 0. So we have our answer of 1/2 sine of 2x. So just a little bit of practice of the idea of just finding antiderivatives. All right, so let's get to today's lesson. So once again, this is day 2 of this topic of optimization. Today we're going to look at a little bit how optimization can come into play in a subject such as economics, and then we're going to finish off with one other type of problem. Okay. So first, a little review in terms of, for those who might have forgotten some of these concepts or are not too familiar with them. First, revenue. So revenue is literally the money that you're making from selling an item or a service or whatever. So like, for example, if you sell t-shirts, the money that the customer is giving you is your revenue for each t-shirt. All right. Cost. Cost is going to be the price of producing said item. So for example, going back to this idea of selling t-shirts, your cost would be the price, would be whatever money you paid to make those t-shirts. Finally, profit, which is something we're going to be looking at today, profit is going to be your revenue minus your cost, right? So how much money the customer is giving you minus how much money you paid to make those t-shirts to begin with. So your profit, obviously, if that number is positive, means you're at a, it's good for you since you're making money. If it's at a negative, that means you're losing money, okay? So let's look at first example 1. So suppose Mr. Mihawk has decided to give up teaching and start a premier lemonade stand. So when I'm talking about premier, I'm talking about like fancy, expensive lemonade. The revenue brought in by the stand can be modeled by R of x is equal to 19x. And the cost by C of x is equal to x cubed minus 8x squared plus 24x, where x represents thousands of cups of lemonade. What production level would maximize profit? Okay, so what production level would maximize profit? So we're trying to determine how many cups of lemonade do we need to sell or produce, in this case, in order to maximize profit. So we're trying to maximize profit. Well, let's find the profit function first. So let's call the profit function P of x. And remember, like I said in the previous slide, profit is just revenue minus cost. So profit is going to be R of x minus C of x. Okay? Well, we're given the revenue function and the cost function in the problem already. So let's actually do that. So the revenue is 19x. And the cost function is x cubed minus 8x squared plus 24x. Okay, and you'll see that I did put this quantity inside of parentheses because we're subtracting the entire quantity, not just that first term. So let's simplify this a little bit. So first let's distribute that negative. So 19x minus x cubed plus 8x squared minus 24x. It looks like we do have some like terms, 19x and minus 24x. So if we were to simplify this, we would get negative x cubed plus 8x squared minus 5x. So that would be our simplified profit function, or simplified profit function. Okay, so we are trying to maximize this function. We're trying to maximize this function. So recall, whenever you're trying to find the maximum of something, you want to take the derivative of that function. So let's do that. Let's take the derivative of p, so p prime of x. So that gives us negative 3x squared plus 16x minus 5. So a pretty straightforward derivative. All you're using is just the power rule. Remember taking that exponent down in front and then just subtracting 1 from the exponent. Okay, so we found the derivative. Now we want to find those critical numbers. So let's find those critical numbers. So we want to set this equal to 0. And we're going to factor this. Now, first, really quickly, to make this a little bit easier for ourselves, let's factor out that negative 1. So let's factor out that negative 1 so that our leading term is positive. So positive 3x squared minus 16x plus 5. Okay. So now we have that. We're going to focus on that quantity, 3x squared minus 16x plus 5. So there's a couple ways you can do this. You could use the quadratic formula, which if you remember it, that's great. If you don't, or if you don't like it at all, what we're going to do here is we're going to factor this. So we're going to find two factors that would multiply to give us this expression. So let's split it up here. So since our leading term is 3x squared, that means these two terms are 3x and x. And now we just have to test different combinations. Now we want whatever we're multiplying to equal positive 5. Positive 5. Now, if you notice, though, it has to multiply to positive 5, but somehow add up to negative 16. Well, let's see. There's only two pairs of numbers that multiply, two pairs of integers, numbers that are integers that multiply to positive 5. Positive 1 and positive 5, and there's no way you're going to add up 1 and 5 to get you negative 16. But there's also negative 1 and negative 5, and that is actually the pairs of numbers that work out. And we can easily check to make sure by, if we were to multiply 3x and negative 5, we would get negative 15, right? 3x distribute, 3x and negative 5, that would be negative 15. And then negative 1 and x would be negative 1. Negative 15 and negative 1 do give us our negative 16x. So that is exactly the factors that we wanted. So now we just set them equal to 0 and solve each individually. So 3x minus 1 is equal to 0. X minus 5 is equal to 0. Add 1, divide by 3, so x is equal to 1/3. Add 5, so x is equal to 5. All right, now we have to determine which of these are actually maximums. We found two critical numbers. Let's see if either of them are maximums. So we do our quick number line test. So 1/3, 5. So let's see. To the left of 1/3, let's try 0. Well, if we plug in 0, we get a negative number times a negative number, so that's positive. Whoops, but then I forgot we had that negative originally in front. So that becomes negative. Actually, let me put it here just to remind ourselves that there is a negative there. All right, let's see, a number between 1/3 and 5. We try 1. 1 is pretty easy, so we're going to try 1. So let's see, 3 minus 1, that's positive. 1 minus 5, that's negative. So we have positive, negative, negative. So that's going to give us a negative. Negative, negative, positive, and then a positive, positive. And when I'm combining these numbers, I'm multiplying them, right? A negative times a negative is a positive times a positive remains positive. Finally, we're going to try positive 6. So let's see, 3 times 6 is 18 minus 1, that's positive. 6 minus 5 is positive. So these two factors are positive, but then it turns up negative because as a result of that negative in front of the parentheses. So it looks like between these two critical numbers, 5 is our maximum, right? Because it's increasing, then it's decreasing since the derivative is negative. Increasing, decreasing, decreasing. So it looks like our max is at 5. So x equals 5 gives us max profit. So in other words, because remember, x represents thousands of cups of lemonade, so sell 5,000 cups of lemonade. So 5,000 cups of lemonade to maximize profit. So sell 5,000 cups of lemonade to maximize profit. So that's what we need to do. Or that's what I need to do in order to maximize the profit of my premier lemonade stand. So once again, nothing too new in this problem. Really, all we did, did I write 5,000,000? Whoops. Sorry about that. Let's erase that. And not 5 million. We don't want to sell 5 million cups. All right. So 5,000 cups of lemonade to maximize profit, which is a lot, but I mean, hey, it's a premier lemonade stand. We need to sell a lot of cups to maximize profit. So there you go. That's how you would do this example. So not a lot different than what we saw yesterday. Just this time we had this idea of a profit function, so we had to do revenue minus cost. All right, so let's look at the next one. Excuse me. So using the same cost function as example 1, how many cups of lemonade would Mr. Mihawk have to produce to minimize the average cost per cup? So now I want to minimize the average cost per cup. Now the thing you do want to be careful of here is, okay, well, it talks about average cost of cup. So we're not trying to minimize the cost per cup. We're not trying to minimize the cost. We're trying to minimize the average cost per cup. Well, the average cost function is actually not very difficult to find, right? In order to, if you just think in general, to find the average of something, you take the total and you divide it by the number of things, right? Well, for us, the total is just C of X, so average cost. The total is just C of X, right? That's the total cost, or how much it would cost us to produce said number of cups of lemonade, and we want to divide it by the number of cups. Well, the number of cups is just X, right? The number of cups is just X. X represents the number of cups of lemonade. So that's what we're going to do. We're going to take that cost function, which was x cubed minus 8x squared plus 24x, and we're going to divide it by x. So we're going to divide that by x. So this is pretty simple. We're literally just taking out a power of x from each of these terms. So this becomes x squared, this becomes 8x, and this becomes 24. So that is the average cost function. The average cost function is x squared minus 8x plus 24. So that is the function that we're trying to minimize. So So that is the function that we're trying to minimize. So that is the function whose derivative we will be taking. So let's just call that function a of x. So a of x. And we want to find the derivative of that. So a prime of x. So this is pretty simple. So 2x minus 8. So that's our derivative. We want to find the critical number. So set it equal to 0. So add 8 divided by 2. So add 8 divided by 2. So x is 8 divided by 2, which is 4. So let's just make sure, let's verify that this is indeed a minimum. So we got a 4 there. And remember, we're plugging in these values into the average cost function. So let's plug in 0. So if we plug in 0 into here, we get 0 minus 8, so that's negative. Now let's plug in 5. If we plug in 5, we get 10 minus 8. That's positive. So that is indeed, that is indeed a minimum, right? We wanted a minimum. We wanted it to decrease, then increase, right? Decrease, then increase. So that is indeed a minimum. So, produce 4,000, because remember, X is in thousands of cups of lemonade. So produce 4,000 cups of lemonade to minimize average cost per cup. So as you can see, the answers from our previous two examples, they're not the same, right? We actually maximize profit. We maximize profit if we sell 5,000 cups of lemonade. We minimize average cost at 4,000 cups. So this is a perfect example of a real-life situation where you're not necessarily maximizing your profit when you're minimizing your cost, right? Because in this real-world example, even though we would have minimized our average cost, in this case, in this situation, our revenue probably would not have been maximized. Our revenue would have been smaller than had we sold 5,000 cups of lemonade, which makes sense. So, in a situation like this, right, our numbers did not end up being the same, which in real life that's going to happen, right? Just because you're minimizing your average cost does not mean you're maximizing your profit necessarily, because you might be lowering your revenue at the same time. So just a little example using economics. So revenue, cost, profit. So now let's look at our last example. So this one is a little bit more, oh no, the picture's not here. Okay, I know the picture's on your handout. Guess I forgot to put it on the PowerPoint. So we have a rectangular page that is to contain 24 square inches of print. So let me actually draw that picture that's on your paper. So your picture looks something like this. So that's your paper. And then the print is a certain section. Okay. So the blue section, the area of that blue section is 24. And on your papers, let's see, it's listed as, this is X. Nope, that's Y. Actually, it doesn't really matter, but we just want to be consistent with what's on your notes already. So this is Y. And then this part is X. So basically, the length and the width of just the print area is X and Y. And then the margins at the top and bottom of the page are to be 1.5 inches. So we have, so this is 1.5, and this is 1.5. So once again, I'm just redrawing the picture that's on your papers. And the margins on the left and right are to be 1 inch. So this is 1 inch, and this is 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So the least amount of paper is used. Okay, so we want to use the least amount of paper. So in other words, for the print to use the least amount of paper, right? The print to use the least amount of paper. So that's what we're going to try to figure out. All right. Well, let's see. Well, so we're trying to use the least amount of paper. Well, what is the area of this paper? So least amount means the area of the paper. So the area of the paper. So we'll just call it as area. Well, the area of the paper, according to our diagram, the area of a rectangle in this case is just length times width. So the area in this case would just be x plus 3 times y plus 2, right? So x plus 3, y plus 2, because the length, here we go. Ooh. The length is going to be x plus 1.5 and 1.5, so that's 3. And then the width is going to be y plus 1 plus 1, so y plus 2. All right. Well, remember, we're not done here. So that's the equation or the function that we want to minimize. So least amount of paper, right? In case that wasn't clear, least amount we want to minimize. So what's our second equation? Because remember, we don't want to take the derivative of this function until it is in terms of just one variable. Well, we're also told that the print is 24 square inches, right? The print, so just the blue part of the paper is 24 square inches. So that means, so just the area of that rectangle is 24. Let me do it here. So the area of that rectangle is x times y, right? Because the print part, according to our diagrams, the length is x and the width is y. So now we can solve this equation for y by just dividing both sides by by y. By x. By x. So we're going to divide both sides by x, so we get y is equal to 24 divided by x. And we're going to substitute that. So we're going to substitute this into y for this equation. So let's do that. So now we have x plus 3 and 24 over x plus 2. So now we have an equation just in terms of x. And remember, this is the equation that we want to find the minimum of. So this is the equation that we're ultimately going to find the derivative of. Now, before we do that, let us simplify this a little bit by distributing. So let's distribute. So we have x times 24 over x. So that's just 24. The x's cancel out. X times 2, 2x. 3 times 24 over x. So that's just 3 times 24 over x. So that is 72 over x. And 3 times 2, so that's 6. So we'll combine some like terms here. So we have 30 plus 2x. That's a 0, sorry. Plus 72 over x. So this is the function that we're taking the derivative of. And just a reminder, before we take this derivative, remember 72 over x is just the same thing as 72 times x to the negative 1 power, because we're going to be using that power rule when we take the derivative. So let's take the derivative. So a prime, whoa. Guess I pressed too hard. So the derivative of 30 is just 0. The derivative of 2x is just 2. And now we have the derivative of 72x to the negative first. So the exponent comes down, so 1, so minus 1, times 72, subtract 1 from the exponent, so x to the negative second. So I'm going to rewrite this as 2 minus 72 over x squared. Okay. So this is the function that we want to minimize. So let's find those critical numbers, set it equal to 0. So let's get back up here. So 2 minus 72 over x squared is equal to 0. Let's add 72 over x squared to both sides. So 2 is equal to 72 over x squared. Multiply both sides by x squared. So 2x squared is equal to 72. The x squared on the right side just cancels out. Divide both sides by 2. X squared is equal to 36. And finally, just take the square root. So x is equal to the square root of 36. And the square root of 36 is plus or minus 6. Now, we have two answers here, but the only one we care about, this is similar to that first example we did yesterday, the only one that we care about is x is equal to 6. The dimensions of this paper cannot be, or the dimensions of the paper cannot be negative. Hence that negative 6, just remove it. And our only x value is 6, so that is the So since that's the value that should be the minimum. Now, since there's only one x value, that means it's most likely that's the minimum. But let's just verify just to be sure. Let's verify just to be sure. So remember, we're plugging these in to a prime. So let's test out 0. So if we plug in 0, actually we can't test out 0. Let's try 1. So if we plug in 1 into here, we get 2 minus 72 over 1. So 2 minus 72. So that is negative. Now let's try 7. So let's see, let's try 7 now. So if we plug in 7, we get 7 squared is 49, 72 over 49. That's going to be less than 2, so 2 minus a number less than 2 is going to be positive. So now, that is indeed the minimum as we wanted. That is indeed a minimum as we wanted. So now, we're almost done. We're almost done. We have to find the dimensions of the page. We want to find the dimensions of the page. So x is equal to 6. X is equal to 6. So that means if x is equal to 6, if we look onto here, if we use this formula right here, if x is equal to 6, that means y has to be equal to 4, because that's the only way that can be equal to 24. Whoop, and I ended up right at 24. Sorry about that. So y is equal to 4. So now be careful. We're almost done. That's the dimensions of just the print area. We want to find the dimensions of the piece of paper. So that means if x is 6, the length should be 9. So the length is 9. And since y is 4, the width is going to be 6. Okay, so that means the dimensions of this page is 9 by 6 or 6 by 9, however you want to read it. So there you go. That is the dimensions of the page that would use the least amount of paper, a 9 by 6 paper or 6 by 9 paper, however you want to say it, length by width or width by length. So there you go. That was our last example of today. So once again, we just did a few more different types of examples today. We didn't really see anything that was new. With the previous 2 examples, we didn't have to deal with a second variable, but as we saw with this third example, we had an x and a y, and we had to eliminate that y variable, which we did by using this 24 is equal to x times y equation. From there, take the derivative, find the critical numbers, verify that it is indeed a minimum or a maximum, and answer the question. All right, so that was our second day of optimization. We still have most likely one more day where we'll look at a few more examples. I will be attaching an assignment that will look just like the previous assignment, just 6 more problems using optimization that will go with this lesson. So try it out if you want to. Otherwise, I hope this lesson was clear. If it ever is, if any lesson ever is not clear, always make sure to let me know. Otherwise, I hope you guys are staying safe. I hope you guys are staying healthy, taking care of yourselves. Otherwise, I hope you guys enjoy the rest of your days. See you later.